Good morning. Welcome to our very first online lecture on applied solid mechanics. Okay, so today we are going to discuss stress transformation. Okay, by right, if you check your course outline, our first chapter should be strain transformation. Okay, strain transformation. Okay, strain transformation. Okay. However, I strongly suggest if we go through this chapter first and then we will go to our original first chapter, strain transformation. Why I do so, it is because that once you clearly understand with the idea of stress transformation, it will be very helpful for you to go to get clear understanding on strain transformation. Okay, if we notice the keyword of this chapter is stress, and then transformation. So what does that mean? That means that we are studying the stress characteristic, on an object, which is transformed maybe due to the rotation of the xy axis. Okay, so basically in our applied solid mechanics, we are referring to the stresses that are acting on a single plane. Okay, let's say we have an element. Okay, so this is our element. Okay, and then at the same time we have a defined x-axis and y-axis. Okay, so on this single element, we will have two different normal stresses. The first one is normal stress sigma x, which is defined with respect to the x-axis. And then the second one is the normal stress sigma y, which is defined with respect to the y-axis. Okay, and then at the same time, we will have shear stress. Okay, shear stress, which is denoted as tau xy. Okay, so this means that we have three stress component. Okay, stress component on a single plane. Okay, so what plane? Plane x and y. Okay, so and then other important thing about this stress transformation. Okay, so we have to go through the definition of the state of plane stress. Okay, so we write down here. Okay, the state the state of plane stress. Okay, plane stress, the state of plane stress at a point at a point at a point can be represented. Okay, can be represented. Okay, can be represented by two normal forces. Not normal forces, two normal stresses. Okay, which are sigma x and sigma y. Okay, two normal stresses. Okay, two normal stresses and one shear stress and one shear stress. One shear stress. Okay, so these three stresses. Okay, sigma x, sigma y, and then shear tau xy will be different. So what happened? That means the value is changing. Okay, will be different. Will be different for each specific orientation of theta. Oh, suddenly we have a theta here. So where this theta come from? Okay, so I will explain after this. Okay, so for each specific orientation theta of the element at the point at the point. Okay, so back to the theta. Okay, so where this theta come from? Okay, so let's say we show the difference. Okay, so this is the initial state. Okay, initial state when theta is equal to 0. Okay, and then this is the new state. Okay, the new orientation. Okay, the new state when theta is not equal to 0. So let's say we define theta is equal to 30 degree, for example. Okay, so this theta is defined at the x-axis and y-axis. So this is our original or our initial xy axis. Okay, so that means the orientation of the element can be drawn like this. Okay, so this is your element. Okay, so this is your small xy plane element. Okay, and on this element you have sigma x. Okay, and then sigma y. And then at the same time, we are going to have shear stress. Okay, only one shear stress, tau xy. Okay, so at this point, okay, at this initial state, the theta is equal to 0. So where the theta is defined? The theta is defined as here. Okay, on this horizontal plane. So at this position, theta is equal to 0. So what happens if this xy axis is rotated counterclockwise with theta equal to 30 degree. So this is your original xy axis. Okay, and then at the same time, your new xy axis is rotated with the theta counterclockwise. Theta. Okay, so this is your new x prime. Okay, so this is your theta. Theta is defined is equal to 30 degree. So this new x-axis is denoted as x prime, and then at the same time the y-axis is denoted as y prime. Okay, so the rotation is not only happen on the xy axis. Okay, so the element also experience the rotation. Okay, so the orientation of the elements, let's use the green color. Okay, so the orientation of the element will tend to be like this. Okay, so I will draw carefully. Okay, due to the rotation of theta equal to 30 degree. Okay, so the 30 degree is defined from here. So this is your theta, which is equal to 30 degree. Okay, and then what happened to our normal stresses? Okay, so our normal stresses will also change. Okay, so this is your new normal stress x, new normal stress sigma x prime. Okay, and then this is your new normal stress sigma y prime. So that means the value for sigma xy prime is not equal to or the original sigma y. So sigma y prime is not equal to the initial state of the normal stress sigma x, not sigma y. Okay, and then similarly for sigma x prime is not equal to sigma x. Okay, and then of course you are going to have your shear stress here. Okay, so this is your shear stress. Again, the shear stress is going to have new value. So this is what we call stress transformation. So this is the original state, and this one is the new state, okay, due to the rotation of theta equal to 30 degree. So that's why we call this phenomena or this concept as stress transformation. The stresses are transformed with respect to the changing value of theta. And then what happened? We are going to have new normal stresses, okay, with respect to the involved axis and also the shear stress. Okay, next, let's go to general equation of plane stress transformation. So I will write the subtitle first. Okay, so again, where's my black pen? It's not appear on the screen. Oh, that's your. Okay, I need an eraser. So we erase this blue color, use the black color. Okay, so we are going to discuss the general equation, the general equations of plane plane stress transformation. Plane stress transformation. Okay, as I mentioned just now, okay, due to the rotation of the xy axis, the value of sigma x is not equal to the value of sigma x prime. Okay, so this sigma x prime only happen when there is a rotation of the xy axis. Okay, the rotation is measured by the theta. Okay, theta. Okay, so before we start discussing a little bit more detail on that, okay, so there are a number of concepts that we need to have clear understanding. Okay, we need to clearly understand. Okay, the first one is sign convention. So we have an agreed sign convention. Okay, sign convention. Okay. So usually in our previous chapter, we agree that for every single vector to the right, okay, x-axis must be positive. Okay, and then for every single vector that moves upward, okay, y-axis, okay, y will be positive. Okay, so what does that mean? Our component, okay, so let's say we are referring to an element. Okay, so let's draw our element first. Okay, so this is your element. Okay, and then we know that the initial state of this element theta is equal to 0. Okay, and then we draw our axis. Okay, so this is your x-axis and y-axis. Okay, for all sigma x, okay, that happen to be in the direction of positive x-axis, the value of sigma x will be positive. Okay, and then similarly for any sigma y, okay, in the direction of y will be positive. Okay, and then for shear stress, okay, that is in the direction to the right top of the element will also be positive. So this is our agreement. So that means if we have this kind of stress profile, okay, so the sigma x is in the opposite direction of the x. So that means the value of the sigma x will be negative. Okay, so that's what does it mean. Okay, next. Okay, so we need to erase this first. Okay, and then we have to clearly understand the normal and shear stress component. Okay, second. Okay, we have already discussed on this, but as a revision, so let's draw again. Okay, so normal and shear stress component. Okay, this time let's define an element, okay, which is rotated at a certain theta. Okay, at certain theta. So that means the orientation of the element maybe will be like this. Okay, so this is the new orientation of the element due to the rotation of the xy axis. Okay, and then here the theta, okay, for example, theta is equal to 30 degree. And of course, we are going to have new x-axis. So this is your new x prime axis. Okay, and then this one is the new y prime axis. Okay, and then for the stresses profile, so this is the positive direction for new sigma x prime. And this one is the positive direction for new sigma y prime. Okay, and then similarly for our shear stress tau xy. So be careful on that. Okay, so every calculation must follow this xy direction. So you need to be very careful with the positive and the negative sign. Okay, so let's continue our lecture. Okay, so now I'm going to show you the most important equation in this chapter. Okay, so let's write down the equation. Okay, again, where's my black pen? It's not here, it's here. Okay, eraser. So erase this blue color. Okay, use the black pen. Okay, so in this stress transformation, okay, there are a number of important equations. Okay, so as we keep discussing before, okay, until now, okay. So we are going to define the new value of sigma x prime, okay, and then the new value of sigma y prime, and then the new value of shear stress tau xy prime, okay. So the general equation in order to determine all these parameters are, okay, so the sigma x prime, okay, so the new sigma due to the rotation of xy axis can be calculated using this equation, okay, which is equal to the initial state of sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. So this will be our first equation. Okay. If we check carefully, so in this equation we have theta. So you are going to use the given theta, okay, where the theta is given from the measurement of from the rotation of the xy axis, okay, and then also you just simply substitute the initial value of sigma x and sigma y, and also there's tau xy, and then in the end you will get the new value of sigma x prime. Okay, so please memorize this equation. Okay, I'm not sure this equation will be provided in your final exam as an appendix. Okay, but I strongly suggest if you try to memorize this equation so that you'll be very familiar with this equation. Okay, and then how about normal stress y prime? Okay, sigma y prime. Okay, by right, okay, we can simply use this equation. Okay, so we can simply use this equation, but you need to refer to the rotation of the theta with respect to the x-axis. Okay, so I will show you an example after this. Okay, so now we will focus on the equation for the shear stress tau xy prime. Okay, for tau xy prime, okay, tau xy prime is equal to minus, so just simply take this portion, okay, and then give a negative sign, sigma x minus sigma y divided by 2, okay, instead of cosine, we define sine theta here, sine 2 theta plus tau xy cosine 2 theta. So this will be your second favorite equation. Okay, so please memorize this equation. Okay, so after this, I'm going to show you an example on how to determine the new value of the sigma x prime or sigma y prime, and also the shear stress tau xy prime due to the rotation of the axis. Okay, so now I'm going to show you an example. Okay, so how can we determine the new value of the normal stresses and the shear stress, okay, due to the transformation of the xy axis. Okay, let's say you are given an element. Okay, so I will draw the element. So I will use, this time I will use red color. Okay, red color. Okay, so red square color box. Okay, so this is your initial state of the element. Okay, and then the profile of the normal stresses, okay, is given as, okay, so this is 80 megapascal. Okay, and then we have 50 megapascal. Okay, and then so the shear stress is given in this direction, okay, which is equal to, okay, which is equal to 25 megapascal. Okay, so let's write down all this value. Okay, so we notice here the direction of the normal stress on this plane. Okay, on this plane, sigma. Okay, let's simply define the x-axis and y-axis first. Okay, so sigma x is equal to minus 80 megapascal. Minus 80 megapascal. Okay, why minus? Because if you check the direction of the vector 80 megapascal, okay, is to the left. Okay, which is to the opposite direction to the x-axis. Okay, and then for sigma sigma y is positive. Okay, it's positive 50 megapascal. Okay, and then at the same time, your shear stress xy is negative. Okay, it's negative 25 megapascal. Why? Okay, so we need to check our agreed sign convention for an element due to the normal stresses and shear stress. Okay, so this is our standard profile of stresses of an element. Okay, so the positive should be to the right. So this is your sigma x. Okay, but this example, it tends to be to the it happen to be to the left direction. So that's why we have minus sign. Okay, and then the positive sign for sigma y is upward. Okay, and then the shear stress is in the direction to the top of the right corner of the element. So this is your tau xy. Okay, and then so again, the positive sign for shear stress, okay, is also to the left corner of the elements. Okay, but in this example, it is in the opposite direction. So that's why we have minus tau xy. So we miss the minus sign here. So be careful on that. Okay, so these are the important parameter. Okay, so let's highlight this parameter. Okay. Okay. And then it is mentioned here, okay, the orientation, okay, the orientation of the new axis. Okay, so the question asks you, okay, so the question asks you to determine, okay, determine the state of stress, okay, of this element once the orientation of the xy axis, okay, theta is equal to 30 degree positive, or no, 30 degree clockwise. Clockwise, C-L-O-C-K y. So that means in this direction. Okay, so the sign of this theta will be minus 30 degree. Okay, so that means if you want to draw the orientation of the element, okay, so this is our original xy axis, okay, and then the new orientation of the axis, okay, with due to the rotation of theta with minus 30 degree, will turn to be like this. So this will be your new axis, x prime, okay, and this one is your theta, 30 degree clockwise. Okay, because we have a minus sign here. Okay, so this is the rotation of the xy axis. Okay, and then this will be your y axis. So we denote here this one as x prime and this one as y prime. Okay, and then similarly, the element will also experience the rotation. Okay, so let's draw the element. Okay, so this is the orientation of the element. Oops, sorry. Where's my eraser? Okay, so we need to draw carefully so that you will have clear understanding on the stress transformation. Okay, so this is your element. I'm sorry, I'm not good at drawing. Okay, but roughly you can understand the rotation of the element. Okay, so the 30 degree. So here is the 30 degree. Okay, so here is your 30 degree. Okay, your 30 degree. Okay, minus 30 degree, or we can also draw like this. Okay, so this is your new sigma x. Okay, new sigma x prime. Okay, and this is your theta, which is equal to 30 degree, and this will be your new sigma y prime. Okay, but the problem here, we do not know the direction of the sigma x and sigma y. So what we need to do, we need to use our favorite equation. Okay, so recall our favorite equation. Okay, so sigma x prime is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. Okay, So since we have all the parameters, so we know the value for sigma x. So sigma x is equal to minus 80 megapascal. Okay, so we just simply substitute the parameter. Okay, sigma x is equal to 80 megapascal. Okay, and then your sigma y, be careful, your sigma x is equal to minus 80 megapascal. Okay, and then your sigma y is equal to 50 megapascal. 50 megapascal. Okay, be careful with the unit. Okay, so sigma x no problem, sigma y no problem, and then your theta here, your theta is equal to minus 30 degree. Why? Because the axis is rotated clockwise 30 degree downward. Okay, so you just substitute the parameter. So this one is also minus 30 degree. So in the end, you will get the value for new sigma x. Okay, the new value of sigma x is equal to minus 25.8 megapascal. Okay, easy, right? Okay. Similarly, for shear stress, okay, so we focus on the stress with respect to the x-axis first, okay, and then for shear stress, tau xy prime, okay, so recall again your favorite equation, minus sigma x, oops, sorry, so I prefer to write again, so let's erase this one, okay, so let's write carefully. Okay, so your sigma xy prime is equal to minus sigma x, okay, sigma x minus sigma y divided by 2, okay, minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy, which cosine 2 theta. Okay, so you just substitute all these parameters. So in the end, you will get the value for the new shear stress is equal to minus 68.8 megapascal. Okay, so next, we are going to calculate to determine the value for sigma x prime. Okay, let's continue our calculation. So we want to determine the value of new sigma y prime. Okay, so before that, let's draw our element. Okay, so this is the orientation of the new element. Okay, after being rotated with theta equal to 30 degree, minus 30 degree clockwise. Okay, so the theta can be defined. Okay, so this is our reference. Okay, reference point. Okay, and then the 30 degree is defined from this reference point to the perpendicular line. Okay, so this is the perpendicular line to the plane, to this plane. So this is your 30 degree. Okay, theta is equal to 30 degree. So this is the direction, or not the direction. Okay, so the value for sigma x will be perpendicular to this plane. Okay, so this is your sigma x. Okay, from our calculation, we know that our sigma x is equal to minus 25.8 megapascal. 8 megapascal. Okay, so notice that we have a minus sign. So once we have this minus sign, so that means the direction of the new sigma x will be like this. Sigma x, it turns inward to the plane, or to this plane. So this is the value for your, this is the direction of your new sigma x. Okay, and then from our calculation, we know that the value for shear stress x prime y prime is equal to minus 68.8 megapascal. Again, we have minus sign here. Okay, so that means the direction will be like this. Okay, so this is your shear stress. So this is the direction of your shear stress. Okay, which is equal to 68.8 megapascal. Okay, so how about sigma y prime? Okay, so this is your sigma y prime. Okay, sigma y prime. Okay, as I mentioned earlier, okay, in order to solve or to determine the new value for the sigma y prime, you can also simply use the equation for sigma x with respect to the x-axis. Okay, so recall the equation. Okay, so sigma x prime is equal to sigma x plus sigma y divided by 2. Okay, divided by 2 plus sigma x minus sigma y, okay, divided by 2 cosine 2 theta plus tau xy sine 2 theta. Okay, so be careful. This equation only can be used or only can be applied, okay, with respect to the x-axis. So that means we have to define the new theta with respect to the our reference initial x-axis. So this is your initial x-axis. So that means the new theta with respect to the x-axis is here. It's like this. Okay, it's like this. Okay, and then the value is equal to, so this theta, the value is equal to 90 degree minus 30 degree, which is equal to 60 degree. So we can use this angle. Okay, we use this angle in our x-axis equation. Okay, so we substitute the value of sigma x plus sigma y. Okay, so we know that our sigma x is equal to minus 80. Okay, and then the value for sigma y is equal to 50. Okay, but the theta here is 60 degree. Okay, and then be careful here. The sign for the theta is positive. Why? Because we are referring to the original x-axis, okay, to this direction. So the direction is counterclockwise. So that's why we define the theta as positive sign, positive 60 degree. So be careful with that. Okay, so the final answer is equal to 4.15 megapascal, and with minus sign. Okay, with minus sign. So that means the direction of the sigma y, okay, so in this case we are referring to the x-axis, so the direction will be like this. So this is your sigma y, okay, which is equal to 4.15 megapascal. Okay, so we're done with our calculation.